Good morning, everyone, and welcome again to ISIT 2008, Toronto. For those standing outside, I think we're going to get started with the first plenary this morning. I'd like to call to the stage Professor Vince Poor, who is going to introduce our plenary speaker this morning.
Thank you, Frank. Good morning. It's a great pleasure to be here this morning to introduce my colleague, Rob Calderbank, who's this morning's plenary speaker. And it's often said on these occasions that the speaker needs no introduction, but I think that in this case actually is true. But here I am, and Frank introduced me, so I feel like I need to introduce Rob anyway. So here we go. So as many of you know, anyone who's spoken with Rob knows, he grew up in England. He was educated at Warwick and Oxford universities. And then he taught high school for a year before joining Caltech as a graduate student, where he worked with Marshall Hall, who was also, by the way, the advisor of Donald Knuth. He graduated from Caltech in 1980 with his PhD in mathematics. At that time, he joined Bell Labs as a member of the technical staff. He rose through the ranks. He became an AT&T fellow. I guess this was after the split. Then he retired from AT&T. Looking at him, it's hard to believe that he actually is retired. In 2003 as vice president for research. While he was at AT&T, as of course I think most everyone here knows, he twice received the IT Society Paper Award. I think very few people have achieved that distinction. And he also served as the editor-in-chief of the Transactions. So after AT&T, in 2004, Princeton was very fortunate that he came to join us, where he's currently professor of electrical engineering. In fact, his office is just next to mine. Mathematics and applied and computational mathematics. He's also director of the program in applied and computational mathematics, so he has many hats at Princeton. He's also been recognized in many ways at Princeton. Both within and without the university, he was elected to the U.S. National Academy of Engineering in 2005. And last year at Princeton honored him with its Graduate Mentoring Award, which is a student-initiated award in Princeton for graduate student mentoring. So, Rob, as again, most of you know, works at the intersection of mathematics and electrical engineering, and primarily in the field of information theory and coding. And in this area, he's made a number of fundamental, profound contributions to, first, to voice line modems, more recently to space-time coding, so, sort of the internet, the beginnings of the internet, wireless, and also to the future, quantum error-correcting code. So he's done an enormous amount of work that's been very important. And more recently, he's again head of the trends, and we're going to hear, I think, some about this today. He's been exploring the mathematical foundations of active sensing. Rob is great at anticipating trends, as you can see from the work that he's done. And one of the things that I heard about Rob was that one time back in the 90s, when cellular and GSM and so forth were just taking off, he went to visit Nokia in Oulu, and they took him snowmobiling. And according to one eyewitness, Rob promptly crashed into a tree and bruised his ribs. So perhaps anticipating the dangers of connecting cell phones with driving, well before the rest of us. So anyway, in addition to these accomplishments, as again many of you know, Rob is an outstanding expositor of technical material. So I'm very much looking forward to hearing his talk today. And please join me in welcoming Rob Calderbank.
Well, thank you very much, Vince, for that very kind introduction. I should say that the theme of the talk is blurring. And I could wish for transparencies that were a little crisper, but I think that there are still some seats further forward if you'd like the crisper view. So I'd like to thank the organizers for the invitation to talk here this morning. It's much appreciated. I should also thank my sponsors, the Mathematics Division at NSF, the Air Force, the Navy, and DARPA. I'm going to tell you a story today about Golay, Heisenberg, and Weyl. The applications context for the story is active sensing radar. Along the way, there'll be connections to space-time coding and to quantum error correction. We won't be able to explore those connections in any great detail. We'll just point them out as they pass. Now, I should also acknowledge my collaborators, and I'd like to give a special thanks to Stephen Howard from the Defense Science and Technology Organization in Australia. Every time I think that I'm finally getting to understand radar, Stephen sorts me out. Bill Moran from the University of Melbourne, Electrical Engineering Department, and Ali Pazeshki, who is currently a postdoctoral fellow in the program for Applied and Computational Mathematics at Princeton, and who will be joining Colorado State in the fall as a tenure-track assistant professor in electrical engineering. So, information theory and coding date from 1948. But measurement is actually a much older subject. Hamming codes, discovered by Hamming in 1950, but the duals of these codes, the first-order Reed-Muller codes, they were actually discovered by Fisher in 1942 in the context of his work on experimental design. Earlier still is the work of Frederick Yates on weighing designs. So for Yates, you're given some kind of measurement device, and it's got zero mean and some variance, and you're given n objects. And you want to measure each of those objects with variance sigma squared over n. You can, of course, measure each object multiple times, but it's actually more efficient to measure objects in combination, and that's what Yates was concerned with. This idea of measuring objects in combination is a very powerful one, and it's a feature of some of the most interesting work that's happening these days in detection and estimation. And so I'll single out the single pixel camera that was developed by Rich Baranyuk and his group at Rice. So here you have an image, and down below you have a microarray. And by pointing the mirrors in different directions, you can take different linear combinations of the pixels. Now, this is an idea that has roots that extend back in time, and we're going to follow one of those roots that involves Golay. So Golay was interested in far infrared spectrometry. And in the middle of the 20th century, far infrared spectrometry was a kind of twilight zone. In between stuff that you could do easily optically and stuff that you could do easily with microwaves. And this gap is the subject of the review paper that he wrote in 1952. Now, he actually published two designs for far infrared spectrometers that worked at room temperature. One involved taking combinations in the time domain, that's the spinning disks, and the other involved taking combinations in the frequency domain, and that's the one that we're going to talk about today. So why was this hard? Well, three reasons. What Golay was trying to do is he was trying to understand molecules by looking at the way that specific chemical bonds absorbed energy, radiation. And the sources were really weak. There was a ton of background noise, and he had really poor detectors. These detectors were just temperature sensors. They just integrated radiation across a big band, and they weren't able to discriminate between different frequencies. Now, spectrometry is about diffraction. So radiation at different frequencies appears at different angles. And the way that you discriminate is with slits. And if you have a narrow slit, you can discriminate pretty finely, but you don't get a lot of energy. If you have a fat slit, you get a lot of energy, but you can't discriminate. Golay found this really cool way of making fat slits work. And Golay's apparatus involves prisms and all sorts of stuff, and I've just abstracted what's going on mathematically. What he does is he takes the radiation from the source, and he splits it into two paths, corresponding to two binary sequences, X and Y. And on each path, the radiation goes up against two pairs of input and output masks in parallel. And the binary sequence tells you whether the slit's open or whether it's closed. Now, the radiation that you're interested in presents orthogonal to the slits. And if you look at the first path, the radiation goes straight through because the input and the output masks are the same. On the second path, the desired radiation is blocked because the input and the exit masks are opposite. Now, the background radiation presents at an angle. And so it's shown here in red, and it casts a red shadow on the output mask that is a translate of the input mask. And the sequences X and Y have the particular property that for every angle of background radiation, the amount of energy on path 1 is the same as the energy on path 2. And so you can measure the radiation at the frequency that you're interested in just by subtracting the energy on path 2 from the energy on path 1. And if you think mathematically, what property is it that we require of these binary sequences? It is exactly that the sum of the autocorrelation functions is a delta function. And that's the defining property of Golay complementary pairs. And they're going to be at the heart of the talk. And so I'll animate that property for you. This is as multimedia as we get. You see, we're calculating the autocorrelation function on each side. And the sum is 0, except when the sequences are on top of one another, when we get the spike, and so on. OK. So now that's the history and Golay. And now what I'm going to do for the next little while is talk a little bit about fundamentals of radar with the idea that when I'm done, you all will know enough to be dangerous. So what we're doing is we're illuminating a scene. We're trying to figure out range from the round-trip delay. And we're trying to figure out velocity from the Doppler effect. So let's put the Doppler effect on one side. Just think about range. We're taking the return, and we're matching it against what we sent. We're looking for peaks. We'd like to get an impulse, so we want a main lobe which is narrow and has a lot of energy, and we want to depress the range side lobes. Why do we want to depress the range side lobes? Because let's suppose I was pinging out at the back of the room here. I actually know where the back of the room is. What I'm interested in is the stuff that's going on close to the back of the room. And if I have range side lobes, the reflection from the back of the room is going to obscure the stuff that I'm trying to see. So range side lobes are a bad thing. We'd like to get rid of them. Now let's bring Doppler back in. Again, we take the return and we match against what we sent. Instead of an autocorrelation function, we have an ambiguity surface. And the ambiguity surface expresses the blurriness of the scene with respect to this match-filtered way of processing. Now, we'd like a thumbtack, but that's not possible. There's a fundamental identity due to Weyl, which is the Heisenberg uncertainty principle in another guise, which places a lower limit on the volume of the squared ambiguity surface. So there's an inevitable volume that a radar engineer can't avoid. And in a sense, the job of a radar engineer is to send this inevitable volume places that don't matter to the operational role of the radar. That's what waveform design is. Over on the right-hand side here is a picture of the ambiguity function of a barcode of length 13. Down below is half of the ambiguity surface, the left half. The black line in the lower picture is the zero Doppler line. And so you actually see the range side lobes of the Barker sequence in black at the bottom there. Now, engineering practice is largely about getting to modularity. And what we'd like to do, which is standard practice in radar, is to send a pulse train of waveforms. Here we're just going to send the same pulse over and over again. And what we want to be able to do is express the ambiguity function of the entire pulse train approximately in terms of the ambiguity function of the little component waveform. And if the things that we're looking at aren't moving too fast, if we can actually ignore Doppler at the chip level, we can do that. In this talk, we're going to be thinking about phase-coded waveforms. So these are just like spreading sequences in CDMA. So really all they are. So they're going to be sequences either of plus or minus 1 or plus or minus 1 plus or minus I. Here are some popular sequences, Frank codes, Barker codes. You can see their range side lobes. Here's the Golay complementary codes. See, they don't have any range side lobes at all. And as far back as 1960, Welty had looked at this picture and he'd said, gee, these would be really useful in radar. And now, if you look around at any radar system in the world, you will not see a Golay complementary pair of waveforms. And the reason is that every practicing radar engineer knows that they don't work. And so I'm actually going to spend the next 15 minutes or so talking about something that's known not to work. And hopefully at the end of 15 or 20 minutes, I'll have persuaded you that it might work if you did it in the right way. So, what's the problem? this is a picture of the ambiguity function of a Golay pair. The quote on the right-hand side is taken from standard text on radar by Levinon. And this is Levinon saying very politely that Golay pairs don't work. And why don't they work? And the reason that they don't work, naively, is Doppler. So you might be looking out at a bunch of trees, but you're not interested in trees. You're actually interested in people moving in the trees. And the problem is that the stuff that you know about has side lobes in Doppler bins that you're interested in because there might be things moving in those Doppler bins. So the trees create range side lobes with Doppler that obscure the things that you're trying to see. And so in this picture, there's a vertical black line down the center. Black is good because that's no side lobes. And that's the Golay complementary property. But there's also these hotspots that are off of that central line. And those are bad because they're masking things that you want to see. And mathematically, the problem is that when you introduce Doppler, you no longer have a delta function. Here's another view of that same problem. So this is a simulation of what I understand is a representative surveillance radar. What that means is that I think I'm not supposed to know what all the parameters are. What I do know is that it works at about 17 gigahertz. Here we're trying really hard. We've got 256 pulse repetition intervals. So 256 of these pulses. By the way, the way that you should think about pulses is think of pulses as being about a microsecond long, and think about these intervals as being about 100 microseconds. So we pulse, and then we listen for a while, and we pulse again. We've got Golays. I think they're of length 64. We've got 256 of them. We've got 3 strong scatterers, and we've got 2 weak scatterers, and weak is about 30 dB down. And you can see that we work really hard, and it's still pretty tough to see them. And we're going to try and do better by using time as a degree of freedom. And here I should say there's a very nice paper by Mark Bell which introduces waveform adaptivity in the context of pulse train design. It's published in the IT Transactions around 1998. So what we're going to do here is we're going to use the freedom to choose different waveforms in this pulse train. What we're going to do mathematically is we're going to take the ambiguity function, we're going to look at its Taylor expansion around 0 Doppler, and we're going to try and kill moments. Because that will correspond to Doppler resilience. So let's start by killing the derivative. So here we have 4 pulses, 2 Golay pairs, and let's think about the derivative, the first order approximation. Well, we can simplify this sum of correlation functions by using the fact that because x2 and x3 are a Golay pair, their sum of their autocorrelation functions is a delta function. So we're left with a delta function plus autocorrelation of x1 and autocorrelation of x3. Well, if we impose the further condition that x1 and x3 were a Golay pair, we'd kill that too. We get a Doppler function. We get a delta function. In general, you can think about taking these components, x and y, and sequencing them using a binary sequence P. And on the left-hand side here, I've collected the terms that go into the main lobe. And on the right-hand side, I've collected the terms that go into the side lobe. And you can see that you can control the size of the side lobe by controlling the spectrum of P. Now, those of you who've worked in magnetic recording on the design of spectral null codes, this is very familiar. And in fact, it's an easier problem. Because in the magnetic recording world, you guys are concerned about rate. I'm just looking for one good sequence. So the key sequence turns out to be something called the PreWay to a Morse sequence, or PTM sequence. And this is built up recursively. So the one of length 2 is 0, 1. To make the one of length 4, you complement the one of length 2, that's 1, 0, and then you stick them together. 0, 1, 1, 0, and so on. There's another use for this sequence. Imagine that you have two dualists, and they're not very good. And you want to organize a fair duel. So your sequence P governs the order in which they're allowed to shoot at each other. And you don't want either of them to have an advantage. PreWay to a Morse sequence is a really good way to organize this duel. It's not actually the best way, but that question is explored in a beautiful paper by Sinan Gunturk. Anyway, the theorem here is that you want to kill m moments. You can do that with a sequence of length 2 to the m plus 1. In the example that we looked at, we had a sequence of length 4. We killed 1 moment. And it makes a difference. So on the left is the picture you saw before, the alternating pulse train, XY, 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 XY. On the right is the 2E Morse sequence. Coding theorists in the audience will have, I think, observed that when I constructed the 2E Morse sequence, that's a first-order Reed-Muller code word. It's just the recursive construction of Reed-Muller code words. And by using other Reed-Muller code words, you can clear out different frequency bins. You can also play games with oversampling. And actually, one of the interesting things about oversampling is here on the right-hand side, I was trying to get a null at 2 pi by 3, but I get other nulls, too, at pi by 3 and 0 of different orders. So that whole process is an interesting one. All right. Now we're done with time. I'm going to explore different degrees of freedom. We did time. I'm going to do polarization and space, and then I'm going to do frequency. So, polarization. I have two channels, in a sense, V and H, vertical and horizontal, two orthogonal polarizations. And I'm going to coordinate how I send phase-coded waveforms on the two channels. And actually, we'll see here an emergence of the Alamoudi space-time block code. I mean, if you're in the wireless communication business, this looks exactly like the way that Lindskog and Poroj implement Alamoudi in OFDM. I'm going to stick today to 2 dimensions. So the 2 polarization dimensions. All of this works in multiple spatial dimensions, too. And there's a generalization. I mean, in a sense, before there was Alamoudi, Alamoudi is a special case of the para-unitary filter banks that were introduced by Tseng and Liu to study acoustic surface waves. And the deal in radar is that, you have these multiple locations. You can write down all of the equations, and in theory, you might even be able to solve them. But in practice, you probably can't. And what's interesting is putting the intelligence into signaling so that detection is really easy. That's why orthogonal designs and orthogonal space-time block codes are so popular. I'm not going to say a whole lot about space, but I did want to say one thing, which is that imagine you have multiple spatial locations and they're all sending waveforms. Those waveforms arrive at a different point in space at different times, right? So a point in space is uniquely coordinatized by the linear combination of these waveforms that arrive. That linear combination gets reflected, it bounces off stuff, but even with all of that multipath, you can recognize the point from the character of the linear combination, not just the time of arrival. So that's actually an interesting thing about spatial diversity in sensing. All right, how does this work? The motivation here for polarization is that it's a lot harder to hide in 2 dimensions than in 1. So objects are characterized by a polarization scattering matrix. So, and this matrix tells you how radiation is reflected. So HVV is stuff came in on vertical and it came out on vertical. VH came in on horizontal, came out on vertical. And over on the right-hand side there, I'm telling you how I'm going to signal on the 2 channels. And I have to tell you what wiggle is. Wiggle is conjugate time reverse. And that matrix there on the right-hand side, x minus y wiggle, y x wiggle, is unitary. And the reason it's unitary is the Golay complementary pair property. Now, unitary is kind of cool, because when you do match filtering in 1 dimension, you always take a loss. Here, we're doing it in 2 dimensions in a unitary way, and it's lossless. We can also get the Doppler resilience. We've eliminated the range side lobes, and just like Alamoudi signal processing, the complexity of detection isn't more, really, than the baseline single-channel system. So we think this is a really cool thing. All right. Now, finally, frequency. So when we were doing Doppler resilience in the time domain, we get greater resilience by doing longer and longer pulse trains. And that's good if the things that we're looking at are well behaved. That is to say, if they're going to stay in the range cell that they're supposed to be in it, and they're not going to change their velocity too much. So that's a problem. We'd like to trade time for frequency, so bandwidth. So we'd like to do OFDM radar. But there's a problem. And the problem is, I ping out on a tone, the return comes back with a phase shift, which is the round-trip distance modulo the wavelength. Now, I want to coherently combine the returns from 2 different tones, but the phase shifts might interfere destructively. In the example up here, they've interfered super destructively. I've lost the main lobe, and all I have is noise. Not a good thing. How can we get around that? The answer, or an answer, but we think a good answer, involves going back to the Golay complementary pair property. So you recall that with Golay complementary pairs, at every lag k, the autocorrelation functions are equal and opposite. So if we square them, they have the same size. Also, actually, if we look closely, there's an extra property which is kind of cool. And that is that both of the autocorrelations vanish at even lags. And what we're going to do is we're actually going to do nonlinear rather than linear processing. We're actually going to make sequences, a pair of sequences, that are complementary with respect to the squares of the autocorrelation functions. The way that we're going to do that is we're going to take one of the functions and we're going to modulate it by I. So we're going to multiply it element-wise by I to the n. So when n is odd and we square, they're going to cancel. And when n's even, we don't care because they started off as 0 anyway. Okay, well, that's nice mathematically, but how does it translate into practice? Well, what you do is you burn some bandwidth. So you transmit each sequence twice, above and below carrier, equally offset. The phase shifts that come back are conjugate, so when you multiply them together, you get something that's independent of the phase shift. And so you can get things that are square complementary. Now, in a way, what we've done here is before we were doing Golay complementary pairs and linear processing. And we've traded that, and we had side lobes to contend with. And we've traded that for nonlinear signal processing and cross terms. And I'm sure we could prove that there's got to be a certain amount of energy in the cross terms. But actually, the important thing about cross terms is that we can send them places. And one of the things that we're going to do in the next slide is we're going to linearly vary the offset. And this is a side-by-side comparison. On the left side is the state-of-the-art processing with a Frank-coded waveform. On the right-hand side is our method. We have 5 really strong scatterers. We have a weak scatterer that is 30 dB down. And as we vary the offset, it becomes apparent. Actually, so this is an interesting picture for radar engineers. And there's a message on the top of the slide. And the message is basically, don't optimize waveforms. And the reason is, you optimize a waveform for a particular circumstance, you will probably never see that circumstance again. But if you design tunable waveforms, and here the carrier offset is a parameter that you can tune, and you can actually tune it to pick out combinations of big scatterers with small scatterers around them. It works really well. Okay, so at this point, I hope I've convinced you that maybe Welty was right, after all, that there is some value to these Golay complementary pairs. And I'd actually like to make 2 points. One is that when you think about radar platforms and how they evolve, you can actually think in terms of generations, just like cellular systems. And successive generations involve new degrees of freedom and new signal processing. Second point that I'd like to make is a lot of the most exciting emerging applications don't have anything to do with defense. So the NSF has a Center for Collaborative Adaptive Sensing of the Atmosphere, which is headquartered at UMass. When you look at the weather on your TV and you see these pictures, there's a network of weather radars across the US. And because of the curvature of the Earth, they only have universal visibility above 10,000 feet. And there's a lot of interesting weather happens below 10,000 feet, like tornadoes. And NSF is augmenting or refining that coarse network view with little radars that are designed to fill out that picture and make for more accurate tornado warnings. And that's a really cool application. And as our planet warms, we expect to see more and more extreme climate events. And getting ahead of those events is, I think, going to be really important. All right, so end of applications. Now we're going to do some mathematical framework. So where do these Golay complementary pairs come from? How can you think about them mathematically? Well, we're going to start off with symmetry group of the square, which is the dihedral group D4, 8 matrices. In quantum computing, this is the error group of a single qubit. So you can think about a beryllium ion. It's got 2 states, spin up, spin down. X is a bit flip. It's interchanging the 2 states. Z is a phase flip. Together they generate the discrete error group of the quantum system. What's important about Z and X is that they anti-commute. If you're a physicist, you always refer to X and Z as Pauli matrices. If you have m qubits, instead of a 2-dimensional Hilbert space, you have a 2 to the m dimensional Hilbert space. Now the error group is Kronecker or tensor products of these little 2x2 matrices. There's a notation that I've introduced here, DAB. So A and B are binary vectors, and the binary string A tells you about appearances of the X matrix, and the binary vector B tells you about appearances of the Z matrix. This Heisenberg-Weyl group is the mathematical framework for algebraic coding theory. It's a really interesting group. Matrices in this group square to either the identity or minus the identity. And pairwise, they either commute or they anti-commute. And there's a little symplectic form that tells you which. That's the A transpose dot B plus B transpose dot A. Now, this is really just Fourier analysis in disguise, right? Because think about Fourier analysis. You've got, let me think about cyclic time shifts, which I'll call delta K0. The corresponding frequency shifts, which I'll call delta 0J. So there's a time shift group and a frequency shift group, and they're interchanged by the Fourier transform. And we have exactly that picture on the left-hand side in the binary world. We have binary time shifts and binary frequency shifts. And they're interchanged by the Walsh-Hadamard transform. And so Walsh functions, you should think of them as sinusoids. Well, because in the Fourier world, sinusoids are the eigenfunctions of time shifts. In the binary world, Walsh functions are the eigenvectors of discrete time shifts. Now, you can ask the question, what are chirps? chirps are second-order read-Muller code words. And how does this work? And there's an so when you have the binary time shifts x, you simultaneously diagonalize them, you get the Walsh function. So you have an orthonormal basis and a big symmetry group sitting above it. The cosets of the first-order read-Muller code in the second-order read-Muller code correspond to orthonormal bases of Cn. And each one comes with a big symmetry group. What's the symmetry group? It's just obtained from the time shift group by conjugation. So down at the bottom, at the level of orthonormal bases, you're just applying a symplectic transformation dp. And up top at the level of symmetry groups, you're conjugating to get the new symmetry group. Now, this dp is an interesting transformation because you can see it's quadratic. So this p there is a binary symmetric matrix. The subtle thing about what goes on in the exponent is that all the arithmetic is mod 4. And so all of the entries on the diagonal of dp are plus or minus 1 or plus or minus I. So when I get my new eigenvectors, they're going to have entries plus or minus 1, plus or minus I. So this is the Z4 representation of second-order read-Muller codes. Okay. Now we're going to change gears a little bit, and we're going to think like physicists. So physicists reduce everything to projection operators. This is great for mathematicians because it means that mathematicians can do quantum mechanics because it's just projection operators. And the operators DAB are an orthonormal basis for operators on this 2 to the n dimensional Hilbert space with respect to the trace inner product. And the Weyl transform just tells you how you take an operator and get to the expansion in that basis. Nothing more complicated than that. Let's build up some intuition. So let's start out with a sequence, a Walsh sequence. And let's build the corresponding projection operator. And let's figure out what its expansion is in terms of these DABs. What's interesting about the expansion is the only things that are non-negative come from the symmetry group of the Walsh functions. It's not a coincidence. We'll do the same thing with the Dirac function. We make the rank 1 projection operator. And when we look at its expansion in terms of the DABs, the only things that enter that expansion are the symmetry groups of the Dirac sequences. So the message is that we can, we're going to go from sequences to rank 1 projection operators, and we're going to be worried about the size of the support of their Weyl transform. And we can make that support be real small by making the symmetry group be real big. So that's the import of the theorem. The other interesting thing is when you look at the cyclic time shifts and you ask how they look in the DAB basis, they look extraordinarily pretty. They are Sierpinski triangles. So the Sierpinski triangle is the union of the supports in the Weyl transforms of all the cyclic time shifts. Now, let's just it's always a little bit messy, correlation, because there's periodic correlation and there's aperiodic correlation. Well, we just go from one to the other by padding with zeros. Won't worry about that too much. Let's think about the Golay complementary pair property. So I start with a sequence, I translate it, and then I correlate. Well, I just rewrite that in terms of operators. And you see that what I'm really looking for is I'm looking to make a sum of two rank 1 projection operators, p theta plus p phi, and I want it to be orthogonal to delta k0. And I'm going to think about that orthogonality with respect to the Weyl transform. Well, this is a very pretty picture. So here, the red and the purple squares. So I'm choosing, this matrix P tells you about the second order Reed-Muller code word. The red and the purple squares tell you about the symmetry group of that orthonormal basis. The black squares in the Sierpinski triangle are the even shifts, the even lags. And you can see that the even lags don't overlap with the support of the symmetry group. That's why the things vanished at even lags. There are some overlaps at odd lags, and we just have to make sure that when we look at the Weyl transform, those coefficients cancel out. It's actually easy to do that. In fact, there's a recipe for picking out the two things in a pair. You start with something in the coset, and then you apply something, an operator, that anti-commutes with everything in the intersection. So that works out very nicely. So there's a mathematical framework for sequence design, which is, I think, really interesting. And now it's time to conclude. Long time ago, Woodward wrote a book on probability, information theory, and radar. And he was inspired in part by Shannon's work. And the book ends with this really heartfelt and very self-depreciating comment. And I think that Woodward was being very unfair to himself. Because, you know, he introduced the radar ambiguity function, which is a big thing. So he says, the reader may feel some disappointment, not unshared by the writer, that the basic question of what to transmit remains substantially unanswered. Well, I hope that I've convinced you that there's cool stuff to do in that area. The blue things are things that I talked about to some degree. The black stuff is another talk. I'd like to leave you with just one final slide. There are a lot of books on coding theory. And I have a particular fondness for books that have a definite point of view. And I have to confess that one of my favorites is the book by Dick Blayhut. And with that book in mind, I'd like to leave you with one final thought. And that is that classical coding theory and Fourier analysis are just reverse sides of the same coin. There you go.
Thank you, Rob, for that, for sharpening our vision. So I think we have time for a few questions. It's hard up here to see what's happening out there, so if anyone has a question, you should raise your hand very obviously. Yeah, I see one there.
To what extent can you just port the waveforms you're designing to field radar? To what extent
So the question is, to what extent can you port these waveforms to real radars? To what extent do you need to re-engineer them? So I'll answer that in a couple of ways. So one thing that we are hoping to do later this year with the folk in Australia is to take their experimental radar out and try out the frequency separation idea. Now, you do make a good point about what you can do in theory and what you can do in practice. There's the Naval Research Lab has a, quote, fully polarimetric radar at Chesapeake Bay. What fully polarimetric means is that if someone gets in the back of the panel and connects this wire out here, you can sort of divide into polarimetric subarrays. That's not quite the same as on-demand programmability.
Other questions?
Yeah.
Are there lessons from what you told us that would apply to synthetic aperture radars?
Well, so the answer is yes. I mean, in this talk, I wanted to make a bridge between classical coding theory and Golay and a bit about radars in the middle. And you will, if you're a radar engineer, have noticed that I didn't say anything about the physics of scattering or about those platforms except vaguely. But the answer is yes, and we do think about those things. And we think, for example, that some of the techniques that we've been developing here will work very well for things like space situational awareness and space-based radar where you look down at the ground. Sergio. So the question is, if classical coding theory is Fourier analysis, what is modern coding theory? Well, it's actually a really good question. And you know, I just returned from EPFL where I had to apologize for giving a talk on classical coding theory. And, you know, in the beginning with Shannon, coding theory was about geometry. Modern coding theory isn't really about geometry. It's about writing down a graph with a certain degree distribution. And one of my motivations in exploring this area was to see if there might be a role for geometry in maybe postmodern coding theory. Hope Rudy's not in the audience.
Okay, there's a question in the back right there, I think.
Rudy! No, I think
Okay.
it's just...
Okay, well, please join me again in thanking Rod for that wonderful talk.
That's all right.
You might know of the original